So I request Swami Vedavidyanandaji, the coordinator of and convener of this today's webinar program, to start the session. Maharaj, please unmute your mic.
It is not on. Yeah.
Please unmute. Okay.
No, hello.
Fine. Sound problem.
Aja, I'm just giving a small introduction of Dr. Dr.
Now, first welcome address. First welcome address, then you can.
And all the students of our college, Ramakrishna Mission Vivekananda Centenary College, Chakraborty. So, a small introduction about the speaker. Diptarka Chakraborty is assistant science, national engineering from IIT Kanpur in 2016. After that, he spent 2 years at Charles University, Prague, Czech Republic, as a postdoctoral fellow hosted by Professor Michael Kauke, and then almost an year at Weizmann Institute of Science, Israel, as a postdoctoral fellow hosted by Professor Robert Krauthammer. His research interests are in the areas of theoretical computer science, more specifically algorithms on large data set, streaming algorithms, string matching algorithms, graph algorithms, and data structures. And the achievements are about at FOCS 2018, and then IBM Research India Outstanding PhD Student Award 2015-16. And his research areas is algorithms and theory. So, without taking any more time, I invite to enlighten us in today's topic. And all the students, please mute your microphone, and then just note down the questions, and they will be all you will be given. Please be attentive. Thank you.
Okay. Thank you, Maharaj, for such a nice introduction, and also Swami Kamaleshanandaji for inviting me to give a talk here. So yeah, it is my honor to present, so give a talk in your college. So let me first share my screen. So can you see my screen?
Yes. You are able to see.
Okay, so then let me start. So today what I have decided to talk about some overview of recent advancement in this domain of algorithm design. So but this title is slightly misleading, I will say, because within such short time, it is, I mean, almost next to impossible to cover all the recent advancement. But I will try to cover as much as possible, or at least some of the interesting dimensions where actually people are currently exploiting in this domain of algorithm design. So let me, and also by the way, so I'm not sure about the background of all the students, so that's why I tried to make this talk as much as possible, simple as much as possible, and also I put very few technical things here. So mostly this talk will be non-technical and very simple, so I guess everybody will understand. So I will not talk about any particular result or anything, but mostly I will give some suggestions that which of the areas are currently very exciting and people are exploring. Okay, so let me start with the definition of algorithm. So what is an algorithm? Perhaps we all already know. So an algorithm is a finite sequence of well-defined instruction to solve some computational problem. And the objective is to design an efficient algorithm. So when we say efficient, so how do we measure efficiency? So there are several notions. So, but there are two which are most commonly used. So one is the running time and another is the space usage by the algorithm. So when you run your algorithm, so then in your memory, so whatever space is needed, so that is measured as space usage. So let's now talk about just running time in this talk. And I will not talk about the storage space much. I mean, I will mention here and there about the space complexity, but mostly I will talk about running time. Okay, so what is the trivial way that we analyze the running time of an algorithm? Well, so one obvious way is first implement your algorithm. I write a program and then maybe run your program on your computer, so basically simulate, and then measure the running time. So then the problem will be in this approach is this is, first of all, this is machine dependent, and secondly, it is input dependent. So what do I mean by machine dependent? So for example, so if I run a certain program in my highly configurable some desktop in my office, then maybe it runs for say 2 seconds. But when I run the same program in my laptop, where the configuration is much worse than that in the desktop, so now maybe it takes 10 seconds. But this is exactly the same algorithm. So, but now, so when I say the time of this algorithm, running time, then which thing should I mention? This 2 seconds or 10 seconds? There is this ambiguity there, right? And so another thing is like when you design some algorithm, and so I first design some algorithm and claims that okay, so my algorithm runs in time 2 seconds. Then you wrote some algorithm and run your algorithm and claim that oh, my algorithm is much faster than yours because mine runs in 1 second. But then I say that okay, so give me your algorithm. I run in my desktop and show you that see yours is taking 5 seconds, so mine is much faster. So that's why somehow we need some unified approach to define this running time so that we can compare different algorithms irrespective of which machine we are running this algorithm on. And then the second thing is over input. I mean, for some input, maybe your algorithm run much faster, or for some input, maybe your algorithm takes much longer time. Say, for example, say suppose you want to just check a very simple thing that whether a number is prime or not, and you are given a huge number, say 32 bits number, and now suppose your number ends with 0, so then maybe your algorithm will be super fast. It just say that oh, it cannot be prime. But if it is something else, some non-trivial number, then maybe your algorithm needs to do some clever tricks, and which will be very time consuming. So that's why for certain inputs, your algorithm may run much faster, and for certain inputs, it may run much slower. Okay. So, and that's the reason why we need some kind of mathematical analysis. when we talked about this running time. So now when we talk about some mathematical analysis, what we need is some kind of, we have to abstract out our machine model. We need to somehow define some model of computation which will be completely mathematical in nature, but it should also close to the real computer. So in real computer, you can see that you have your disk, then your RAM, then your processor. So your model of computation should capture all of these things. So one such model that researchers defined or introduced, I guess, I don't know when, maybe late 50s or early 50s sometimes nearby, so which is called the Wardram model. Yeah, I am not sure about this time frame, but at some point of time, so at least 50, 60 years ago, so they defined this Wardram model, which nicely captures this real computer. So here there is this RAM, and then there is this processor. So your input data lies on your RAM, and your program is also lying on your RAM. And then your processor interacts with your RAM. And then when you need to perform certain instruction, say, remember, so when I defined algorithm, I say that algorithm is a finite sequence of well-defined instruction. So now each instruction, so they are now obviously lying on this RAM because your whole program lying on this RAM. And now what it does to simulate one instruction, it first fetch some operand and first decode the instruction, then fetch operand, then perform this arithmetic or logical operation, and then store back the result into the RAM. Yes, I am not going into technical details here that how it actually simulate or anything, but yeah, just to convince you that this is very close to the real computer, so that's why I put this diagram here. And now the assumption is that each elementary operations or instruction like multiplication, addition, subtraction, and or not, all this thing should take some unit cost. So in real computer, actually they take some few cycles, some constantly many cycles. So that's why it is completely fine to assume that they are unit cost. Okay. Now, how do we measure the running time in this model? Well, so I will just count the number of instructions that this runs in. If we run your algorithm on Wardram model, so how many instructions will be executed? That will be counted as your running time. Okay, that is good, but this is a completely mathematical term. I can count the number of instructions. But as I mentioned that your actual running time is actually machine dependent. So what about the influence of these parameters? So there are different instructions, say multiplication and addition. It cannot be the case that both takes exactly same time. Or what about the architecture of your machine, whether it is 32 bits or 64 bits? Also, there are this code optimization due to compiler. So there are different languages which you can use: C, C++, Java, Python, everything. So your algorithm is not dependent on that. So you can implement your algorithm in whatever language that you like. So and there will be dependency running time on this your choice of this programming language. And also there is this multitasking in the operating system. So your running time, actual running time.
Hello. No, join the lecture.
Okay, so let me continue then. Yeah, so what about this influence of this several parameters? So to find the exact influence, you have to run experiment. Otherwise, there is no way that just by counting the number of instruction, you will capture all these influences.
Hello? Tell me. You joined the lecture. Why are you late? I don't know.
Okay, so yeah, so you have to run experiment to have a sense of this influence of this parameter. But luckily, so this parameter doesn't have much impact on your running time of your algorithm, since all these things actually affects your running time just by some small multiplicative constant factor. So for certain machine, maybe this constant factor is 2, some machine may be 3, some machine may be 4 or something. So that's why it doesn't hamper much. And that's why it is completely fine if you count your running time as just the number of instructions. And as I mentioned earlier, so the nice thing about this definition of running time is that it is completely mathematical. You don't have to simulate to analyze your running algorithm. Okay. So now your actual running time is dependent of two things. Firstly, this number of instruction, and it is proportional to that I just mentioned in the last slide, that actual running time will be some constant factor times this number of instructions, and also the input. So that I also mentioned earlier, that for certain inputs, your algorithm runs much faster, certain input, which may run much slower. So generally what we do in the algorithm design, we consider worst case scenario. So that means when we say that our algorithm runs in certain time, then we actually that for no matter whatever be the input, your algorithm must take that time, at most that time. So that's the worst case running time. So there are other notions like average case and all. So those are dependent on the distribution on the inputs. But let's not talk about that today. Let's so throughout this talk, whenever I talk about running time, I actually will mean this worst case running. Okay. So now there are several classical problems on which we are interested in designing algorithms. And these classical problems involve several basic objects like graphs, strings, integer, geometric data, and so on, several other things. So yeah, as I mentioned earlier, that it is almost next to impossible to cover all of this within this short time period. So that's why most of this talk will just talk about the graphs. I'll not talk about strings and integers and geometric data and all in this talk. So let's now introduce what is graph. I'm sure that all of you already know, but just to make sure that we are already in the same page, so let me define it quickly. So now imagine this map of India, which consists, you can see all the national highways. I don't know whether it covers all the highways, but at least this is what I found on Google. So now you want to find the shortest route between two cities. Say suppose you want to go to Delhi from Kolkata. So what is the shortest route? So that means, so here the problem is, given a network of road that connects various cities, your objective is to find the shortest route between any two cities. So now try to think about this problem. How do you attack this problem? How do you solve it? Yeah, so I'm not going to solve this problem in this lecture. There are certain standard algorithms, but this is just a flavor of some problems related to graphs. So now this road networks you can abstract it out as, or define as a graph. So now this graph is an object which consists of several nodes or vertices, and now between each vertex there will be edges. So a graph consists of a set of vertices and edges. So I denote V as a set of vertices and E as a set of edges. And what is the relation between this set of edges and vertices? So E is just a subset of V cross V, because any edge will be between two vertices. Okay, so that's why, so although I mentioned in this slide that I denote G by this double V and E, but I don't think that I have used this notation in this talk. But that is what generally people use when people talk about graph G, they denote it by this double V and E. Okay, so there are two types of graph. One is undirected, and as the name suggests, undirected means that between two vertices, when we have an edge, so there is no direction. So this is like a two-way road. And then there is this directed graph where there is an edge, which you can think of like a one-way road. You can go from, say, 0 to 1, but you cannot go back from 1 to 0 if you have a direction from 0 to 1. So yeah, so as you can see in this picture, so there is an edge from 0 to 1, so you can go from 0 to 1, but you cannot go back. Okay. So there are certain classical problems. One is reachability or connectivity. So in the reachability, so you are given a graph and you are given two vertices. You want to find that whether there is a path from S to T. And you can define this problem both in the directed graph or the undirected graph. And there are standard algorithm, BFS, DFS, Dijkstra. You can solve this problem. And similarly, you can define shortest path problem, which I already introduced on this road network. And depending on whether your graph is unweighted or undirected or directed, or there is a negative edge weight cycle or not, so there are different algorithms, standard algorithms. Those are generally covered in your algorithm course, undergrad algorithm course. So this algorithm includes Dijkstra, Bellman-Ford, Floyd-Warshall, and so on. And then there are these problems called spanning tree. So spanning tree is basically a tree that covers all the nodes in a connected components. And then there are several algorithms to find the minimum spanning tree. Yeah, I'm not going into the definition of this problem because anyway, those will be irrelevant for this talk. And then there are other problems like vertex cover, maximum independence rate. So why actually I put this last two problems here, so that will be clear when I go to the end of my talk. So there will be certain slides that I dedicated just for this last two type of problems. Okay. So these are the classical problems that you can find their solution in your textbook. So now what about multiple queries? So in the reachability problem, say, so what the query means here, so your input is a graph and your query you can think of like this tuple S and T, where you want to find that whether T is reachable from S or not. And similarly for shortest distance. And now what do I mean by multiple query? So multiple query means that your graph is fixed. And now there are several ST pairs which appears as a query. Say for example, so here is an road map of Kolkata. Suppose you are driving and you are using Google Map to find the shortest distance. That is what people use, I guess. If somebody is not aware of all the roads in certain city. So now you can imagine, so in your Google Map, there are several queries. So maybe at some point of time, you want to go to some place, say maybe Behala, from somewhere, say Baliganj, or maybe somebody wants to go to Shambazar to somewhere, maybe Shialda. And now people are just giving these locations, pair of locations as a query and try to find the shortest distance. So now here the thing is that your graph is fixed. Input graph is fixed, but the queries are different depending on this pair of locations. Okay. So how do we solve problems on such scenarios where there can be multiple queries? So I mean, it will be really very bad. I mean, if you want to solve the standard textbook algorithm for each such query, because maybe, I mean, the thing is that maybe you know certain things of your input graph once you have one query. So yeah, so our main objective is to solve each of this query very efficiently. So we cannot take time something like 1 minute to compute a shortest distance between two locations. So that's why what people do is that when your input graph is fixed, they construct a data structure which is maybe much smaller in size than your input graph, because generally your input graphs are really huge. And then when you do place your query, it will access this data structure, not the original input graph, and answer all your queries. So now there are certain things. So first important thing is that when you are given an input graph, you have to build this data structure. So now there's time involved in it, so which we refer as pre-processing time. And then the other parameter is like what is the size of the data structure, and then certainly the square time. And ideally, we want to minimize all these terms, pre-processing time, size, as well as square time. So in general, what happens is there actually will be a trade-off between the square time and size. I mean, generally, it happens that if you allow your data structure size to be huge, then your query time becomes very small. So you can think of like you can pre-compute the shortest distance between all possible locations. So then maybe your data structure will be of huge size. But then your query will be super fast when you place certain location pair. So you just check in that data structure that, okay, so what is the shortest distance? But if you want your data structure to be small size, then you have to do some non-trivial task during your query. But yeah, so this is our main objective, to minimize all three things. So there are certain standard problems like reachability oracle. So where your query will be this, just checking that whether 2 points are connected or not, and then this distance, which is like computing the shortest distance, and then there is this term spanner, which gives you approximate shortest distance. So for many application, I mean, it is completely fine that if you don't compute the exact shortest distance, I mean, you can think of like, I mean, what does it matter that if you reach some point, some location, say within 10 minutes or maybe 10 minutes, 30 seconds, right? So those two paths will be like almost same. So that's why you can take any of these paths. So that's why for certain scenarios, I mean, it is completely fine to compute some approximate shortest distance. So there are huge literature on each of these problems. So I'm not going to tell you all of this, I mean, what is known and what is not. So, but yeah, so as the title suggested of this talk, I mentioned that some overview of recent advancement, but these are like classical problems. So now let's come back to the original topic of this talk. So let's go beyond classical. So the classical problems are on the static model, so-called static model, where basically your input graph is fixed. So but this is not the case for several applications. And also there is another issue that generally your graphs are of huge size. So maybe you can not access your graph multiple times. Yeah, so let me explain each of these things in the next few slides. So Yeah, so just coming out of, motivated from different applications. So there is one model that researchers defined that is called dynamic graph, where basically your input graph is changing. So you can think of one application like, so again, you are driving and you are using Google Map. So now while computing the shortest distance, your Google Map should also take care of these issues like traffic jam, road blockage, or maybe when you start from your house, maybe some road was two ways, but now certainly police restricted it to just one way. So then your Google Map should find it out quickly and give you some alternate route. Yeah, so that's the motivation, that your graph is changing, and how do you now answer your queries? So now the problem remains exactly the same. So your input graph, I mean, there was this initial input graph, and then you build a data structure. Now there are queries like as before, but now there are these extra updates that if something becomes there was some traffic jam, maybe your time to travel certain paths will becomes much costlier, so you want to avoid that. And also maybe if there are road blockages, so that means like, so that road is completely removed out of your road network, you cannot access that now. So now according to this update, you want to update means this insertion and deletion of your edges. So you want to update your data structure, right? So that you can answer multiple queries. So that's why now instead of just query time, you also have to consider update time. And again, you want to minimize all of these quantities here. Okay. So this is one motivation to consider this dynamic graphs, and all these problems that I defined for this classical static setting are still valid for this dynamic model, and researchers are investing enormous amount of time to solve these problems. So here the main objective is to basically beat the whatever be the current base bound for the static model. I mean, you can always run your static algorithms here. So for each update, after each update, you can just freshly recompute the data structure. So, but the non-triviality here is that you want to avoid that, because generally that reprocessing takes too much time. You want to quickly update your data structure. So now, apart from this dynamic model, there is also another model. So, okay, so when I actually say dynamic model, so it is not like that recent. I mean, it was defined something like in 80s, but it consumes huge attention recently from say 2000 or something, or late 90s. But now there is another type of networks which are like faulty networks, which is some kind of, you can think of like special case of dynamic networks, but it needs some different type of solutions. So now imagine that there is certain failure in the network. So for example, suppose some bridge collapses, but how rare that event is. It is not like every day some bridge is collapsing. And also, like, it is not like at any point of time all the bridges will collapse. Maybe at most one bridge will collapse. So that means there can be one failure at most, maybe, or maybe sometimes two or three, depending on how you define your failure. So you want to update this data structure now once there is the failure. So you can, firstly, you can think of like the dynamic model, where this failure is like deletion of certain edges and you want to update it. But the problem with the dynamic thing is that for most of the problems, currently we don't know that how efficiently we can update. I mean, we have certain algorithms, but those are not like optimal. So that's why, so this is a very special scenario where only each fault can occur. So now can we do something better than what we can do for dynamic graphs? Okay, so let's take an example. So suppose you have a graph. So here, so this is your input graph, and you want to compute connectivity at any point of time. So now in the static model, what suffices is to basically store a spanning tree. And now, so initial graph may have lots of edges, but by definition of tree, there will be a very few edges. And now it is completely fine to query your spanning tree. So, okay, by the way, so when I am talking about the spanning tree and all, I am just talking about undirected graph. I'm not considering directed graph. So now here you can clearly see that, so this spanning tree, you can think of like your current data structure, which is now very small in size. So, and this is completely fine that you can now solve all the queries in the static model. So now what if there is a failure? So say this edge actually gets hit. So there was a breach and it collapsed. And remember that so now you don't have this graph. So in your data structure, you just store this sparse representation of this spanning tree. And now in the spanning tree, since this road collapsed, now you can see that if you now have any query on this spanning tree after removal of this particular breach, now you can see that this node and this node is not connected. So if you query in your, say, Google Map, you say that, oh, so you cannot reach from this red node to this red node. But actually in your graph, I mean, if you consider the whole network, actually you can still go, right? So that means your data structure has some issues. I mean, unless you update your data structure, you cannot get the correct answer. So this raises the following question. So, okay, so how can you make your data structure fault tolerant? So that even after this failure happens, your data structure should give, I mean, without any update on your data structure, it should give the correct answer. So, yeah, so in case of multiple queries in fault tolerant, there is no update now. So your data structure in the beforehand, you have to be clever enough to design the data structure in such a way that even if there are a few faults in your road networks or any network, your answer should be correct. Yeah, so maybe you can now think that maybe this is completely impossible, but that is not the case. I mean, obviously, I mean, if you store your original graph, then this is not an impossible task. But here, the non-triviality is that you are not going to store the original graph. And all these problems, classical problems that people still study in the fault-tolerant model, so like reachability preserver, shortest distance preserver, strong connected components, spanner, and so on. So yeah, again, so there are huge literature, and I'm not going to tell you about all this result because those will be too technical. So, but how actually researchers attack this problem? So first they try to solve the single failure case, that when suppose there are only one failure can happen. So then can you build a clever data structure? And then after once they find a single failure case, I mean, they solve the single failure case, then they want to extend it to dual failure. And after that, they want to go to the multiple failure case. And I will say that it is not always the case. I mean, one way you can think that, oh, so if this is just a single and this is dual, I mean, how hard can a problem be just from 1 to 2? But you can believe me that it can be of completely different problem if you have single failure and dual failure. I mean, hardness will be completely different. So for many problems, I mean, there are certain problems like reachability preserver, I mean, some variants of reachability preserver. If you can find a single failure, solve the single failure case, you can directly get a solution of multiple failure. And similarly for spanner. But it is not the case for all other types of problems. So there are some problems even from going from single to dual. So just this step is super difficult. And we know that for certain problems, the guarantee that we can get for single failure, we cannot get for dual failure. Even we can show that. Okay. Okay, so these are the two problems those people are studying recently. I mean, this fault-tolerant model, I will say, is like much newer than the dynamic model. So for fault-tolerant, maybe for just for the last 10 years, the researchers pay really attention on it. And before that, they did not pay much attention. So now there is also another model, which is called the streaming model, which pops up just because of huge data that we have these days, like your huge road network or internet traffic network, like worldwide internet network. And also you can think of like social network, Facebook and all. So those are like huge insights. And now so there are those underlying graphs for each of this application, but since the graph is like huge in size, you cannot actually read at once. You cannot even, sometimes you cannot even store those graphs in your disk. I mean, if you keep on storing all your graphs, maybe soon you will not have enough space. So that's why researchers model this problem in the following way that, okay, so there are this graph, but this is like you can access them in one pass manner. What do I mean by that? Okay, so let me explain. So suppose your edges are coming one by one. So maybe you have first your E1 edge, then E2 edge. So when you have E1 edge, so that means suppose this is your E1, this is between say vertex 1. Then you have E2 edge. So E2 edge may be from 2 to 3. And then again maybe something E5. E5 is somewhere here. Then you have say E4. E4 somehow say connect. This thing is E4. So in this way you can see. So now you can, so now once you actually reach at this point, maybe you cannot go back and see your previous edges. But so far, whatever edge you encounter, implicitly they defined a graph. And also there are some difficult scenarios happen that maybe at some point of time, some edges get deleted. Maybe you unfriend some of your previous friends in the Facebook. So now that's why, so this link gets broken. Now there is no E1 edge. Okay. So now this is somehow different from the dynamic graph. I mean, if you kindly thinking of that, okay, so this is quite similar, but this is not same as the dynamic graph. I mean, here also we have insertion and deletion. You can think of like each of these edges as insertion and this minus as deletion. But the difficulty here is that you don't know, you cannot store this graph explicitly in your storage space. In your dynamic model, you have a data structure which is small in size, but at some point, I mean, like in some space, maybe in cloud or somewhere, you stored your original input graph. So if you want to update your data structure, you are free to access your original input. I mean, of course, you want to minimize a number of access, but you can access. But in this case, you cannot. Even if you want, you cannot. So, and that makes this model notoriously hard. And the only solution that you could get is like, so once you have this streaming access, I mean, one-way access to your graph, so you can actually store some small sketch. I mean, this is, you can think of like data structure, but in streaming model, researchers call it a sketch. So this is like some short summary of your input graph. You can think of like a short summary. But whenever you want to ask some query, what you can access only is this short summary. You cannot access the original input graph because there is no way you can store it. Okay, so this is the difficulty of the problem, and this is what yeah, it will do. So here the problem is basically given the streaming access, you want to compute a sketch such that it could answer all your queries. And then there are different models, insert only model, insert delete, sliding window. So I mean, insert only is like you don't have this deletion. You only can add some edge. And deletion means that you can delete. And sliding window is something like if you are currently here, so your underlying graph will be all the edges that you can see in this last W size window. Yeah, but those are like technical things. I'm not going into the details, but this is one interesting and notoriously hard model that we are interested in this world of big data. So initially, so when so streaming setting was introduced something like again early 80s, but it was finally formalized in something like 96 or sometime like that. I mean, one of the classical papers on streaming model, I mean, where people actually first time get some formal introduction of streaming, which is by Alon Matthias and Zezebi, and this was a breakthrough, and that's why they even got a Gödel Prize, which you can think of like a most prestigious prize in algorithm design domain. I mean, in general, in theoretical computer science domain, it's the most prestigious prize one can have. Okay, so most prestigious means most prestigious prize on certain result. It is not like a lifetime. Okay, and yeah, so but for graph setting, I mean, it was introduced much later, something like I think mid 2000s, 2005, 6 or some around some time. I mean, people start looking into graph problems on this set. So previously, people talked about lots of numerical data they analyze using this training model. So like counting frequency of your data points or some high frequency data, so all these things. But now from 2005 or 10 onwards, people start looking into all these standard graph problems in this streaming model because currently they are very relevant in terms of applications because of this high internet traffic and traffic network, internet traffic network, and also like social network like Facebook and all. Okay, so let's move on. So I guess I have another 5-10 minutes perhaps. So okay, so let's go to the next part of the talk. Okay, so these are like 3 important models beyond classical, I would say, and now there are other models as well that I have not talked just because of time issues. So like distributed model, massive parallel computations, which are also researchers are studying these days. So in this model, you can think of like your input graph is somehow distributed among several parties. Maybe you have some portion of the graph, your friend has some portion of the graph, and you together want to solve this problem. And again, there are huge literature on each of these domains. Okay. So now, so far, whatever I have talked about is about algorithm design, how to design efficient algorithm. But now let's talk about something that if we cannot design algorithms, so let's talk about some hardness of some problems. So if you go back to 60s, so then actually researchers observed some frustrating thing that there are some certain problems like shortest path, and then there is other similar looking problem, which is the longest path, finding the longest path in a network. You may imagine that why do I want to find the longest path, but yeah, you can believe me that there are some applications where actually you want to find the longest path. Then this minimum spanning tree and traveling salesman problem, which is a huge application. Yeah, so I don't want to go into the definition of each of this problem, but yeah, so how do I actually build this table is basically on the left side, I write some problem, and on the right side, I write some very similar looking problem, but of completely different hardness. Yeah, so there are several problems, and now on the left column, whatever the problems I wrote here, those have efficient algorithms. So by efficient means maybe some quadratic time algorithm, a cubic time algorithm, and those are known from 60s. But on the other side, all these problems which are very similar looking, but they have no efficient problems, no efficient algorithms. And it is not the case that researchers have not invested their time on these problems. They invested lots of time, but still they could not come up with any efficient algorithm. So yeah, so this is really frustrating, and people start asking themselves that what is really happening here? So why these problems are so hard? And that's how people somehow formalize and say that there are this class of problems which doesn't have this efficient algorithm, or doesn't have means that so far we don't know any efficient algorithm. I mean, this was the story for the 1960s, and even today, the story did not change. I mean, they still doesn't have, we don't have any efficient algorithm for all of this problem. Yeah, but what do I, yeah, so, but somehow they have some short certificate. Yeah, so I don't want to go into the details. Maybe, yeah, so for students, you will be taught all about this thing in your undergrad algo class or complexity theory class, depending on the syllabus of your course. And yeah, but the take home thing is that all of this problem is somehow easy to verify. Like if you have a solution, if you are given a solution, you can easily verify, but it is extremely difficult to compute that solution. And that's how people define two classes. So one is NP, which have all these problems that are really hard. And then there is a subset, which is P. Okay, so the problems that are really easy that I denote by this green circle. So this is called the class P, where all the problems that have efficient algorithm, those belongs to this class. And then there are the remaining problems, which is this other portion, non-green portion, which consists of all these hard problems, and that people call NP. And there are other classes which I'm not going into. And now the one of the biggest question in the theoretical computer science domain is whether P equals to NP or not. And there is actually, I mean, if you can come up with a solution, either you prove that P equals to NP or P not equals to NP. So by the way, so what do I mean by P equals to NP? So that means that all of this problem that I just defined in that table, which I say that we don't know so far, no efficient algorithm. So if you can come up with efficient algorithm for any of this problem, even not for all, I mean, if you come up with efficient algorithm for any of this problem, it implies that P equals to NP. And I mean, why you can actually, I mean, it suffices to get efficient algorithm just for one particular problem. I mean, that is another story. But yeah, so this is the case. And even if you, for any certain problem, if you can show that you cannot have an efficient algorithm, if you can show that, so then that implies P not equals to N. And if you could show either of these two, then you will get $1 million prize. And this is, yeah, notoriously hard open problem. Yeah, so there is no need to say that. And there is also not a clear consensus among the researchers that researchers believe that one of them is true. So there are some famous mathematician or computer scientists who believes that P not equals to NP, and there are some famous quotes by them. And then there are other set of researchers who are equally famous or even sometimes more famous. They believe that P equals to N. So, but I would say that these days the current status among the researchers is that most of the researchers believes that P not equals to NP, but a few researchers who are also very famous, they think that it is P equals to NP, just like Bela Bulobas, who is a great graph theorist. He actually in this quote mentioned that once he thought that he already solved P equals to NP, but later he realized a mistake and that he could not fix. Okay. So, and this problem is one of the most intellectual export in the computer science, you can say. And this is also considered as one of the important open problem even in the domain of mathematics. And there are huge number of publications on this topic each year. Okay. So now let me come to the end of the talk, and I will finish by stating one recent advancement. I mean, this NP hardness, I will say that those are like some classical problems. But now there are this emerging field which is called fine-grained hardness, which is like, say, you can think of like this all-pair shortest path problem, which you can solve with n cube time, but can you do much faster? So that is the question. And in this domain, people try to attack those problems, and for some problems, they even able to show that they cannot get much faster than what is known so far. And this is a recent field, I mean, that developed in, say, from 2014 or 15. I mean, there was a work by Indic and his student, and they show that this famous edit distance problem cannot be solved in subquadratic time. And there was a textbook algorithm of edit distance using dynamic programming, which solves in quadratic time. And that was the first real breakthrough in this domain. But yeah, so but all these hardness results are not unconditional in the sense that nobody can say that I cannot solve in subquadratic time, but it actually says that, okay, so if I can solve in subquadratic time, then maybe some other even much bigger breakthrough will happen in some other world. Yeah, so those assumptions that I wrote as an exponential time hypothesis and strong exponential time hypothesis, but those are like very technical things, so I don't want to go into details, and also I don't have enough time. Yeah, so but this is the main idea of this domain. So where people want to assume that for certain problems they cannot solve. So like this famous three-set problem, they assume that they cannot solve in much faster time. And assuming that, they prove that, okay, so maybe for some problem in the dynamic model, even you cannot solve better than what you can do instead. Okay. So now, so how to deal with all these hard problems? So there are several ways. People consider approximation, or they exploit the type of the input distribution. They have us basically assume certain things on the input distribution and show that, okay, for certain assumptions, you can design some much efficient algorithms, although in general you cannot. And also there is even recent, like that evolves in just like 2-3 years ago. So that is like use learning or prediction. I mean, there is this huge domain of machine learning, but previously those are like two disjoint domain, theoretical computer science and machine learning. Now people try to merge them in the sense that, okay, so there are these theoretical algorithms, then using machine learning, can we somehow speed up my thing, although we can show something. I mean, generally in the machine learning algorithms, you can show by running some experiment that, okay, so you can solve certain problems, but most of the time you cannot actually prove mathematically that, okay, so actually it solves that problem. So, but in theory, on the other hand, our main objective is to basically prove that whatever you design that actually solves the main problem. And now in this learning, this algorithms with learning, so there the main motivation is that, okay, so take some help of the machine learning and then still whether you can prove something in theory. Okay. And there are several exciting results actually for the last couple of years on this one. Okay, so now I want to end this talk by giving some small advice on the students. So yeah, so you are now very young students, you are now learning algorithms in your school or school means college. So, but when you want to design an algorithm, you always remember this following thing. So when you first see a problem, so how do you attack that problem? Maybe you want to use some of the tools that you learn in your course, right? maybe some divide and conquer approach. I mean, those are like standard tricks that you will either you already learn those or you will learn eventually in the near future. Divide and conquer, then there are greedy strategy, dynamic programming, and this is like natural approach anybody actually done, and once they encounter some problem. But I must say that actually what you should do instead is like you always attack some problem with completely fresh and unconditional approach. You should not stick to certain strategy. And so for that reason, first of all, you need this fresh and unconditional approach. And one very important thing is that you have to work with example. When you encounter a problem, you take very small example and try to, just by pen and paper, you want to, you just will try to solve it. And then you will eventually actually learn, and you will learn that what is the most difficult part in that problem. And that will actually gives you much more insight of the problem, and that eventually helps you to design some efficient algorithm. And also when you design an efficient algorithm, maybe for the first time, when you design something, maybe you will not get as efficient algorithm as you want, but you should be patient. You learn from your mistake, and nobody actually gets success at the first hand, and nobody can get a optimal efficient algorithm whenever they encounter a problem. Maybe they first find some, they make some progress, and then from that progress they learn something, and then try to make more progress. And that's how, I mean, you have to do this gradually, and you never be patient in this process. And sometimes it happens that it takes years to get efficient algorithms. And as I mentioned, I mean, for some of the problems, I mean, even those are starting from 60s or 70s, so far we don't know any most efficient algorithm. So far we don't have that. So, yeah, so that already gives you something, it tells you something that, okay, so you have to be patient in designing efficient algorithm. And then the fourth thing is that you have to formulate your problem in a theoretical way or mathematical way. You should not view your problem from the perspective of programming. Yeah, so many people have this misconception that algorithm and programming are exactly the same, but they are not. So programming is just like implementation of your algorithm. So but your algorithm design is completely mathematical thing. So once actually, yeah, so actually in the beginning of this year or the last year, sometime I attended this talk by Leslie Lampert, which is again famous computer scientist who win Turing Award, which is a lifetime award, and this is the most prestigious award. This is not even like Godel. So Godel is like for one particular work, but this is like a lifelong work. And he got this Turing Award. So he told a nice thing. So I don't know whether you can see. So I actually took a picture during his talk. So he said that, okay, so don't be brainwashed by programming languages. Fill your mind with mathematics. Yeah. So I guess that explained everything that what I mean by this theoretical problem formulation for a better and clear understanding. Okay, so that's all. So I guess I am also out of time. Sorry for taking extra time. And thank you. Again, thanks for inviting me. And now this COVID situation, I must say to all of the students that you should stay safe and be healthy and practice good habits. Okay, and follow the instructions by the government. Okay, so let me stop here. Yeah, any question?
Now I invite the students to ask some questions based on what you have heard. Okay.
Mhm.
Arpan Singham, Sri Mitra, Prabal Roy. Come on, ask some questions.
Yeah, already question has come. Just I
Acha. Where are the questions?
It is audible? Hello, it is audible?
Yeah. So I can hear.
Yes, one question many have come from our live streaming. Many students attend. First question, I think, first question from Niladri Sarkar.
Mhm.
He asked, please explain the programming of data structure.
Sorry, can you?
Please explain the programming of data structure.
Uh, yeah, sorry to say, maybe, yeah, I'm not understanding this question. What do you mean by programming the data structure? Yeah, so I don't know, what do you mean by that, Niladri? So, but I assume that you want to say that how do I build data structure? I don't know. So if you mean by that, so I should say that, I mean, there is no clear cut way. I mean, that highly depends on the problem. Say, for example, so if you go back, so here, say, for reachability oracle, so depending on this problem, like whether you want reachability oracle or distance preserver or spanner, there's different data structure. So there is no unified approach. And I actually guess that there cannot be any unified approach because these problems are, I mean, although here, whatever problems I list down are quite similar in nature. So like, for example, so if you construct a data structure for distance preserver, then of course, that will also give a solution for reachability oracle and also for spanner. But of course, so when maybe for just for spanner or reachability oracle, you don't have to use the power of distance preserver that much. Maybe you can relax slightly. So that's why maybe you can get a better size bound for the data structure. Yeah, I don't know that whether you wanted to know this thing, but yeah. Okay.
Another question from same Niladri Sarkar. He has asked, have any division in multiple queries?
Sorry.
Have any division
In division.
any division, division, division,
Okay. Uh-huh.
multiple queries.
In division, I mean, do you want to say that whether in division problem you have multiple queries?
Yes.
Okay, so if that is the case, yeah, so you can of course have, I mean, today I mostly focus on the graph theoretic problem, so that's why I never talked about division and all. So when you have set of integers and you want to find a data structure, well, that is the most natural problem I can think of currently. Maybe you are given a set of integer and your query will be whether something is divisible or not. Yeah, so that you can have. And it will depend on the application. I mean, if some application demands that, then of course those things needs to be solved. And I'm sure that there are some efficient algorithm for that.
Another question from Sundeep Pramani. He asked, what does running time means?
Okay, so yeah, so that is okay. So that I mentioned in this first few slide that when you hear this term running time, the most obvious thing is like how much time it takes when you run a certain algorithm. Okay, so how do you implement an algorithm? So when you design an algorithm, so now you implement it using some programming language. So you write a program and then you run it on your machine. And then the most obvious thing that you can think about this running time is what is the time it took. in your machine. But then I mentioned that there are certain problems if you define running time in that way, because those will be machine dependent. And that's why researchers introduce this machine, some abstract machine model, which captures all the difficulties of real computers, but still those are mathematical in nature. And now, so when in algorithm design, we talked about running time term, we never say that whether it is the actual running time or not. Like if you run in your machine, whether your things take really that much time. Instead, what we count is the number of instructions. So if you think of this algorithm, so these are like set of instruction. So maybe first statement say that, okay, do something like A plus B. Then the second thing say maybe do B minus C. So all these are like instructions, right? Single instruction. Now you have to count the number of instruction that actually performed in your algorithm. And that is defined as the running time.
Next question as asked by Orkojit Bera. The total time taken by your program to complete a task, especially considering the worst case.
So can you repeat this thing?
The total time taken by your program
Yes.
to complete a task,
Yes.
especially considering the worst case.
Again, I don't understand the question here. So if you, yeah, so this is, yeah, so that is, I guess, is the same as this actual running time versus this running time defined as a number of instruction. And yeah, so I also mentioned that when we define running time, we generally consider worst case input, and that is what you can imagine of like your whatever you just said, the total time taken by your algorithm on or program by worst case input. So that actually we want to capture as our running time, worst case running time.
Thank you, sir. Another question asked by Niladri Sarkar. What is your suggestion for a data science lover?
So for a data science lover, so I don't know at which level you are. If I can assume, can I assume if you are a bachelor student? If so, then maybe.
Bachelor student.
Yeah, okay. Yeah, so maybe you should first try to concentrate on a few subjects like mathematics, statistics, algorithm design, and also programming. But I will not give much focus on programming, because I would say that this programming is the most easiest part among all of them. So that is my personal viewpoint. Many people may disagree. But yeah, so the most important things are mathematics, statistics, especially statistics, part of the mathematics that you need to focus on currently, and also the algorithm design, mostly for the algorithms that actually handle big data. I mean, one thing I also mentioned in today's talk, that is the streaming model, which also captures this big data thing. So yeah, you have to study all this thing. There are huge literature and there are lots of materials available on internet, and also you can ask your professors. Yeah.
There are actually many questions that come because our time is short. We could not address all this, and it is our great pleasure that you have participated in this webinar from Singapore, and it is very lucidly you have described all this programming and its intricacy and its advancement so lucidly that any layman he has no understanding about algorithms, about data structure, about all this, he can easily or she can easily understand. So many students also from behalf of the student, I also request that the student sometimes maybe contact you to know better. That please enlighten them and
Yeah, sure.
they are very much satisfied, and some are also writing what you are telling, because your deliberation is so nice. They are actually give this feedback in this live streaming chat. So, sir, from on behalf of this college, I once again give you the heartiest thanks, and actually also you are very busy person. Still, you give for us a special time to deliver this webinar. So, once again, in future, we also expect you to be present in such a type of webinar and enlighten us and give us enthusiasm, so that all students can those are in computer science and data structure and in other related fields, they will get some inspiration from you. So with these few words, I like to conclude, sir, and also on behalf of participants, once again I thank you and your effort to enlighten all the participants.
Yeah, so I also want to thank you for inviting me, because it was a great honor to be here and talk to you. And yeah, okay.
Yes, sir. So any student, if want your email ID, shall I give or not?
Yeah, sure, you can give.
Because they are very much enthusiastic to join you.
Yeah. Okay. So one request I would like to have. So can you please send me? So you are recording, right? This session.
Yes, recording. It is in recording. It is in YouTube recording.
Okay. So can you send me some YouTube link or something where actually I can find this thing?
Today, evening I send it.
Okay, sure. Thanks. Thanks a lot. Okay.
So now let us leave, sir.
Okay. Yeah, sure.